Okay, let's move on to question 2. So question 2 reads, the speed of light is 3.0 times 10 to the 8 meters per second. If the wavelength of red light is 5.0 times 10 to the negative 7 meters, what is its frequency? So this is a very direct sort of question. We're just given some information. We need to do a calculation with it. So let's list out what we've had. First off, speed of light is this, so let's write that in. V equals 3.0 times 10 to the 8 meters per second. And we're also given a wavelength, so lambda equals 5.0 times 10 to the negative 7 meters, and we are asked to find frequency. We can see then we are dealing with the wave equation again. Let's write that down then. V equals f lambda. And if we rearrange this, I prefer to rearrange, we will get that f equals v over lambda. Okay. Some people prefer to put the numbers in then rearrange. However, I prefer to rearrange the algebra first. There is no right or wrong way, it's what you're comfortable with. Let's substitute 3.0 times 10 to the 8 divided by 5.0 times 10 to the negative 7. And if we put that into our calculator, we'll get an answer. Now, a couple of quick check steps. We've got a 10 to the 8 divided by 10 to the negative 7, so a big number divided by a very small number. So we should get a bigger number than what we started with. If you put this in and you're not careful with your brackets, you'll get 6. Now 6 is obviously not right, because 6 for a frequency is exceptionally low energy. So it would be way, way, way lower than radio waves. This should tell us that it's going to be around 10 to the 15, 10 to the 14. And the answer is actually 6.0 times 10 to the 14 hertz. And if you're not getting that on a calculator, check your calculator processing. Note I have 2 decimal places because both my questions here, or both bits of information here, are also 2 decimal places. Always keep the same precision. Always have to use the lowest level precision you have. Okay, question 3. For this one, we're not actually given any numbers. We're told find the frequency of light emitted from the common laboratory laser. You'll find the wavelength of the laser marked on it. Now, I have a green laser, so green is about 520 nanometers, so let's use that for our wavelength. Wavelength equals 520 nanometers. Now, we've got a metric prefix, converted to SI units, 520 times 10 to the negative 9 meters. But there's no other numbers. We're asked to find the frequency, but we don't have anything else. So the clue is that we're talking about light, and it says find the frequency of the light. You have to recall that the velocity of light is 3.0 times 10 to the 8 meters per second. Okay? And in this case now we're solving frequency. Now the solution at this point is the same as before. We have a formula, F equals V over lambda. We can substitute 3.0 times 10 to the 8 divided by 520 times 10 to the negative 9, and we'll get an answer that is roughly similar to the one before. So we've got 10 to the 8 divided by 10 to the negative 9, but we've got a 10 to the positive 2 there, so that would make it 10 to the negative 7. So again, we'd be around the 10 to the 14 margin. Let's chuck that into a calculator. 3 divided by 1.2. And we would get 5.7 or 5.8 times 10 to the 14 hertz. Okay, so try it out with a couple of different wavelengths as well if you wish to. Let's move on. Question 4. So here now we've got back to some numbers. The frequency of a 5.0 meter sound wave in water is 300 hertz. What is the speed and the period of the sound wave in the water? Okay, so let's list out what we've got here. We've got that F equals 300 hertz. But we've also got that 5.0 meter sound wave. Well, it's a length of distance, that means it's a length of some sort, and so it's reasonable to assume that what's actually talking about the wavelength of the wave. So let's use that. Lambda equals 5.0 meters. Okay, so while this is an assumption, as part of learning how to read the questions, we can check this in our answers at the end and make sure that it is a correct assumption. And we're after two things this time. So we need our speed, our velocity of our wave. It's moving in a straight line, so speed and velocity is the same thing. And what is the period? Now the symbol for period, remember, is capital T. So let's have a look at that. Well, we've got V, we need V, and we've got F and lambda, so that's our wave equation. Let's solve that. V equals F lambda equals 300 times 5.0 equals 1,500 meters per second, or 1.5 times 10 to the 2 meters per second. Now remember, the 10 to the 2 is placeholder, so it's not significant. Two significant figures, because we had two significant figures here. Okay, always keep the lowest level of significance. But what is the formula to work out period? Our period is defined as the length of time it takes for one wave to happen, while frequency is defined as the amount of waves that happen in 1 second. They are inverses of each other, the per second and the second. So we just need to do the inverse of frequency. That would be 1 over 300, which would give me 3.3 times 10 to the negative 3 seconds. Okay, again we can see 1 divided by 100 would give us negative 2, 1 divided by 3 is 0.33, put them together we get 3.3 times 10 to the negative 3. Okay, now question 5 is talking about an earlier question, so do find that in your textbook. It's back a couple of pages on page 287. We have a wave. Let's draw that out. So our wave looks something like this, and at the start it's got a bit of a resting point there before the rest of the wave happens. Now we've got 3 wave crests, 3 troughs, so let's draw that in. 2, 3, back. Let's label our points B, C, D. Oops, F comes after E, G, H, I, J, K, L, M, N. And we've got a row of points at half amplitude, OP, Q, R, S, T. Okay, so let's have a look at the question now. So the question asks, we've got this figure 13.8, it's a transverse wave. The wave is travelling to the right, so let's label that on. So if it's travelling to the right and it's transverse, then the direction of motion must be perpendicular to the direction of, the direction of oscillation must be perpendicular to the direction of motion. If it's moving to the right, then the wave must be moving up and down. And we want to know, well, what is point B, G, P, D, and M? What direction is their movement at this point in time? So I'm going to skip B. I'm going to do G and M first. These are the two simpler ones. If we have a look at G, we can see that it's at maximum amplitude. It's as far away from the middle point as possible. The only place it can go is back in. Okay, so we can say that, well, G must be going back down, and by the same logic, M must be going back up. Let's have a look at P and D. Now, I'm going to draw how the wave might look, say, a second later. So if it's moving to the right, then we need to repeat the wave to the right. Let's just draw one wave there. So P at this point, at time 0, is here. The red line we'll say is time 1, so it's a second later. So where is P moving? P is moving upwards. If we look at D, we can see the same thing. D is also moving upwards. Now B is the troublesome one. If this bit here at the start, where it is, where the wave is not, the question is, well, is that creating the wave so that the next things that happen at B will look like this, or is that's just where the wave has finished and B doesn't actually move, because this wave as an entirety is going to move this way. So if we take that this is where the wave is being created from, then B will now move down. But if we say that B is where the waveform has finished, we could also say that there is going to be no movement. The textbook says B would go down, but to me you could argue both of these quite convincingly. Okay, let's move on to question 6 and look at some superposition. Now, superposition is quite tricky to do by hand. These sort of questions, the way they're presented, would not be good exam type questions. An exam type question would have to give you some numbers so that you could actually draw an accurate wave. So we've got this first wave and we're going to add this other wave. Things of note: firstly, they're in phase. They are on the same side, which means they're going to constructively help each other. They're going to make each other bigger. The second thing, the width of them looks to be about the same in the textbook, so we can just label them over the top of each other. The two together would look something like that. Okay, if we have a look at B, we see B has a square wave and a round wave. Again, they look to be the same size and they are in phase. They are on the same side of the wave. So we can just add the two pieces like so. Okay, let's go to have a look at C. Now, C, we've still got two waves in phase. They look to be the same width, but now one of them isn't square, so it makes it a little bit harder for us to draw. So let's draw our two separate pieces. That looks a bit too wide. That looks okay. So at the start and the end of the wave, they're both at 0, so they're still going to go to 0 at start and end, but in the middle it's going to go up a lot more, and so we would end up looking something like that maybe. Again, not really easy to draw curves by hand for this accurately, so it wouldn't be a good exam type question. As long as you can see why it would just be a bigger curve, then you're doing okay. D now. Now D, we have two waves. They are out of phase. One is below and one is up. And the one that is up doesn't seem to be finished. So I'm going to assume it finishes there. The other thing about D is, to me, it looks like that second part of the wave is actually narrower than the first part. So I think it only is going to affect the first half of that wave. So let's draw our wave shape will go in there, which means that the ending will have something like this, and because the start has nothing here and a lot here, it's going to go straight up. The question is, what happens here in the middle? Okay. This bit is going to be pushed up to there, so it's going to finish about here. Let's draw a connector and then straight down. I think this looks pretty reasonable, but again, if I wanted to do this properly, I would need to use some sort of graph paper with actual values that we could extrapolate from. Okay, question 7. Now, question 7 is using those images there on the side of the textbook. Now, I'm not going to draw them all, so let's talk through them. If we wanted to draw the resulting wave for A and E, there's not going to be any difference. They are not the waves are not interfering with each other. There's no superposition happening. So A and E is irrelevant, and they're not affecting X either. B, C, and D, though, those three are going to interfere with each other. There's going to be some superposition happening here. So let's do that. Let's start with C. Now, look at C. We can see that it is a mirror image either side. Okay? They both have the crest right in the middle, or the trough right in the middle, right around the X. Near either edge, they look to be of the same amount of divergence away from a middle line. So if we were to draw those on top of each other, we would get that it's just a straight line. And X would be stable in the middle. Let's have a look at B. Now, B, we've got parts of the wave are not affecting each other. But the right around X, if we look above and below, we see that it looks to be the same amount above as it is below. So if we were to draw this, let's draw that, X is going to be right in the middle. We're going to have a gentler curve up, a gentler curve down, and then it's going to be a pretty quick change through. But again, that would be point X and it wouldn't move. Now B and D, same principle. They've flipped around and D's a little bit more overlapped than B, but again, look above and below X, we can see, yep, it looks to be the same amount above and below. And so if we were to draw that in, it would look something like that. And again, we would have X there right in the middle. So therefore, X does not move, which is what the point of that question is about. Okay, so let's have a look at our next questions. Question 8, 9 and 10 are all data interpretation type questions, so this would be your IP skills. Things to note: what are the axes? Right? The first one here, we have displacement on the y-axis in centimetres, consider the units, and on the x-axis we have time in seconds. And for question 9, we have distance on the x-axis in centimetres again, so they will change, be careful with that. So let's draw up our graph first. We've got 4 waves happening, 2 waves. That's time in seconds, that's displacement in centimetres, the symbol for displacement is S, and we can see that the top of the wave goes to 20 centimetres, that's important, and here it crosses at 0.3, 0.6, 0.9 and 1.2 seconds. Okay, so A, what is the amplitude? Amplitude is the distance from the mean to the top of the crest, or mean to the bottom of the trough. We only care about the size, not the direction. So in this case, we can see that amplitude is just 20 centimetres, or 0.2 metres. Okay, B. Now B, we want the period of the wave. Definition of period, remember, is the time it takes for one wave to happen. So if we start at 0, we go one whole wave before it repeats, we see that 0.6 is not 0.3, that's only half the wave. So 0.6 seconds, and the last thing it asks for is, well, what is the frequency of the wave? Before we saw that frequency and period were inverses of each other, so this is just going to be 1 over t equals 1 over 0.6 seconds, and if we chuck that in, we will get that. We are about 1.67, or rounded off 1.7 Hertz with 0.6. Let's round that off just to 2 decimal places there. Okay, let's move on. Question 9. Again, we have a graph. Let's draw that in. 1.5 waves, but this time we have that this is distance in centimetres, and this is still displacement in centimetres. So do be careful with that. It peaks at 15 centimetres, and here we have 40, then 80, and then 120. Okay, so part A, what is the wavelength? So wavelength is the distance from either start to the first repetition or from peak to peak. Let's see, so if we're starting here at 0, we see that it is 80 centimetres by the time it gets back. If we have a look at the graph, we see that this 20 and 100 would match up to the two crests, crest to crest, 20 to 100, difference is 80 centimetres again. So 80 centimetres or 0.8 metres. Okay, let's move on to B. B is asking about the amplitude, same as before. Distance from x-axis to the peak is 15 centimetres. or 0.15 meters. Okay, last thing it's asking, or got a bit of extra information here. If the wave is travelling to the right at a speed of 80 centimeters per second, find the frequency of the disturbance. So we're told that V equals 80 centimeters per second. Let's convert that to SI units. So 80 centimeters per second. We need to convert centimeters to meters. The per second here is fine. How do we convert centimeters to meters? We divide by 100. So that would be 0.80 meters per second. So we know that we're talking with V equals F lambda. We have lambda, we have V, we need F. F equals V over lambda equals 0.80 divided by 0.80 equals 1 hertz. Okay. And if we did it with centimeters per second divided by centimeters, make sure we had the same units to cancel, we would again still have 1 hertz. So it didn't matter if we converted or not, but some questions will get tricky for that. Now question 10 we can see has 2 graphs. I'm not going to draw them both, so make sure to be looking at them as we work through this. So the first part of it, these first two are pretty simple. So let's start off with A. What is the amplitude of the wave? Well, amplitude, have a look at your graph, we can see that the crests are peaking at 20 centimeters. Okay. B, what is the wavelength? Now our x-axis is distance in centimeters, which means we can just read off the x-axis what our wavelength is. If it starts at 0, one full pattern finishes at 40. The other parts of it, well, if it went from 20 to 60, or if we went from the middle 10 to 50, and the same thing that we've seen on the second one, 50 to 90 or 60 to 100, all of these come back that the wavelength is equal to 40 centimeters or 0.4 meters. Okay, now C is where we need to start thinking about the second graph as well. We're after the velocity of the wave. Now, normally we'd go, well, V equals F lambda, but we don't have an F here. There's no information about any sort of frequency. We do have a time, but the time here is showing us the distance that something moves. So we have to use our version of speed equals distance over time in order to figure this out. And because it's a wave moving in a straight line, speed and velocity is the same thing. So it moves some distance in 0.2 seconds. How far does it actually go? Well, if we look at the start of the wave, it started at 0 at 0 seconds. At 0.2 seconds, it's at 50, halfway between the 40 and 60. So it moved 50 centimeters, where it moved 0.5 meters divided by 0.2. If we divide 0.2 into 0.5, we get that is 2.5 meters per second. Now the textbook has an answer of 2.5 times 10 to the 2 centimeters per second, and centimeters would be -2. The -2 and the 10 to the power of 2 would cancel, and so we have the same answer, but we're in SI units. Okay, so this is all the in-text questions. The next video will have all the end-of-text questions for sorting them out, probably by star size. Thanks, guys.